So hopefully I can get through this in 25 minutes.
You will.
We'll see. We'll see if I feel like taking more time. What are you going to do? This is some work that was originally funded by RAND itself, which is really unusual, but is now being supported by the Arnold Ventures grant. It's work with Andrew, Beth Ann, and Matt, and although Andrew and I are just pretending to be statisticians, Beth Ann and Matt have the correct ticketing. So this actually started out as an issue we came into when we were trying to summarize the literature. One of the goals we had was to synthesize the existing literature on the effects of various policies on gun violence. And it turned out this was much harder than we expected. This is an example of the kind of problems we run into. So these are several studies that are all looking at the effect of the same set of laws implemented in basically the same states. There might be slight differences because there's slight differences in the years. And as it turns out, virtually identical data. They're all analyzing the same murders. Although I think that at least one of them might use a different data set than the others, but they're basically the same murders. And the same states implementing and the same outcome, you would expect some convergence on the effects, but you find anything from a 5% decrease in murders as a result of right-to-carry laws to a 7% increase in murders. And even more interesting, you have a 20-fold difference in the standard errors on the same data, which struck us as possibly implausible, and that somebody might have gotten something wrong. And we can't synthesize this in a normal way because they're not independent estimates. This isn't like a situation where you do meta-analysis where you got a bunch of studies and they have independent estimates. This is all the same data. This is a purely analytic problem, not a sampling problem. I mean, there are sampling problems embedded within it, but the differences here are because they're modeling it differently. And some of these models are making assumptions that are undoubtedly sort of inappropriate for the data, and others are making assumptions that are more appropriate for the data. And you don't want to synthesize this. You want to throw out the studies that are using inappropriate methods, right? You don't want to do some sort of averaging over this. That brings us to the question, well, which of these are the quality studies? Which of these are making assumptions about the data that are appropriate for the data? So we set about trying to understand this, and I think there's sort of two broad ways to look at this problem. There's sort of a traditional way in which you take your statistical model and you try and list out all of your assumptions, which turns out to be really difficult to do. Most people aren't aware of all the assumptions they're making. And then for each one, you might try and do a test of some sort to see if it's how far your data violate the assumption. And of course, since there's a bunch of different assumptions about every method, and two methods may differ on 10 or 20 different assumptions, then you've got to somehow weight these results, right? Like one model might be better on one assumption, another might be better on some other assumption, and you can't figure out which is the right model. Even if you can find a test for all the assumptions, which in often case there is no test for certain assumptions that are sort of standardized, generally accepted. So we decided to take a different approach, which is we don't really care about the assumptions per se. We care about which of these methods gives us the best estimate of the causal effect, right? And so instead of looking at it assumption by assumption, we want to use a simulation to look at the statistical properties of the estimators in the exact data we're going to use, okay? And presumably if you're making accurate assumptions using efficient methods, as estimators, the right method will rise to the top. So specifically, we're going to do simulations that try and look at these different causal effect estimators with respect to 4 criteria. Does it actually yield the appropriate type 1 error? Right. So these are incorrect rejections of the null hypothesis. If alpha is 0.05, we'd like that to be about 5% of the simulations, right? When there is an effect, we wanted to look at how much power it has, what the proportion of correct rejections are. So when there is a true effect, does this method even find it? And this is basically the same assumption. If you're looking at traditional ways of rating estimators, this is like a minimum variance estimator question. Then we look at two forms of bias. One is a directional bias, like a tendency for the estimate to be positive or negative, to say it increases homicide versus decreases homicide. And then there's a magnitude bias, which is it tends to exaggerate or underestimate the error or the effect, even if it is centered on zero. Okay. So the simulation logic, I'll walk through this. We're going to simulate laws in real data. Okay. Then for each simulated law, we're going to run all the models and all the methods to get estimates using all of them, and then we're going to compare the performance. And so, because we simulate laws, we're going to know what the true effects are. So this is the underlying data on which all the simulations are based. This is the total firearms deaths by state. So this is state panel data, which is the most common data being used in this area to evaluate policies. Each line is a state, and we've plotted the mean line here as well. The way the simulation works is we create simulated laws. We first sample a certain number of states at random, and then for each state sampled at random, we sample a date at random. And we say that's the date of implementation of our simulated law. If we take that information and ran it through a model, you'd expect us to find no effects, right? Except 5% of the time you get false positives. Because we know there's no regular relationship between this law data and the underlying trends in all the states. What we can also do is build in a real effect by minimally modifying the real data without really changing the correlation structure or anything. We simply add or subtract an effect on that date, which is the true effect of the law. So we built in what we know to be a true effect. And then we can run the models again and see whether it actually recovers the true effect with bias, without bias, with how much variance, and so on. So that's the general logic of the simulations. We do this 5,000 times for each condition. And then we can look at the distribution of those four quantities I talked about to evaluate which model works well. We actually did this across 3 law prevalence conditions. So it turns out to be very important which model, the performance of the models vary a lot by how many instances you have of an implementing state. We did 3, 15, and 35 because these correspond to the kinds of policies that are being evaluated in the field. The most common policy that's typically evaluated is about 35 states have been implemented. We do 3 different effects. So you can either have a null effect. There's no regular relationship between the simulated law and the real data. There is a positive effect. There is a negative effect. For all the simulations, the magnitude of the effect we build into the data is the same regardless of the type of model, although it's built into the data always in the way that's consistent with the model assumption. So for a multiplicative model, it's implemented through multiplying by a risk ratio, and for an additive model, it's added by adding a constant to the rate. And that's equivalent to what we thought would be a size of an effect that policymakers should care about, which is that the law would save 1,000 or cause 1,000 additional deaths every year. We also investigated 2 phase-ins. One is a 5-year phase-in, which is just a linear spline over 5 years at asymptotes. And the other is an instant phase-in, which is a sort of standard kind of, when the law goes into effect, the effect is instant. Then we estimated a bunch of models. And for every model, we estimated a bunch of ways of getting the standard errors. I'm not going to go over them all here. In fact, the report on this doesn't even go over all of them because there's just lots of them, and lots of them are really bad. But the important dimensions are we looked at the link function and the likelihood function along with that, and you look at OLS estimates on rates of firearms death. You can look at log rates estimated with an OLS. And that's probably, in this field, the very most common method is to use a linear model on logged outcomes. You can also do Poisson or negative binomial on a count model with, to get to rates, you use the log of the population as an offset. You can, for some of these, you might want to look at population weights for the linear models. They're not nationally representative, analyzed at the state level, and so you might want to make them nationally representative to get effects in the population. So you could apply population weights. You can include lagged effects to make it an autoregressive model. Several people in the literature have done that. You can include state fixed effects or state random effects. You can look at state-specific linear trends in cases where you add state-specific effects. We can look at GEE-based estimation. You can look at standard error adjustments for clustering by state. You can look at standard error adjustments for deviations for the assumed distribution of the residuals, but not the independence assumption. And you can also look at the way you code the model when you use an autoregressive model. Let me talk just a little bit about this because this isn't obvious to most people.
This one still works.
Okay.
It's back.
Oh.
This one
This is like a test. So when you're doing time series panel data, and you use what you call a levels model, like a difference in difference model, you would typically code the effect with, like, it's often just called dummy coding, where it's a 0 in all state years where the law wasn't present and a 1 in all state years where the law is present. When you use a first differences model, which is rare in this field, you would use change coding, which is very similar to effect coding, except because you're differencing the outcome year over year, to get an unbiased effect of the estimator, you have to difference the coding for the law. So if effect coding is 0 in the years it's not and then turns on 1 forever, to get the change coding, it's just the change year over year because the outcome is the change year over year. And so that would be the coding for change coding. The reason this matters, even though we didn't test first differences models, is because we do test autoregressive models. And one of the unrecognized features of autoregressive models is that they can take on either a levels model or a first differences model and be identical to those models depending on the autoregressive coefficient. So when an autoregressive coefficient is 0, your autoregressive model is actually just a plain levels model. When your autoregression coefficient is 1, it is precisely equivalent to a first differences model. And so you probably would have wanted to code your effect in the way that gives you unbiased estimates for first differences model. As it turns out, the firearm death data we're analyzing has an autoregressive coefficient of 0.9, which is going to tell you something about where we end up on the simulation. As it turns out, in this field, we don't know of any papers that have used change coding for the effect of the law. They're all using effect coding, as far as we can tell. Sometimes they don't tell you how they code the data. Oh, I think this is an older slide. Somehow I didn't get the last version up. So all the models have the effect built in, either as change or effect, and that is done either as an instant effect or as a phase in over 5 years. In all cases, it corresponds exactly to what we built into the data. So we're literally using the same function to build the effect into the data that we're trying to use to recover the effect in the model. We have, because all the analyses here use covariates, we include a broad range of covariates, although because they're really collinear, we reduce that set using principal components analysis because we don't actually care about any of those coefficients. And we had fixed effects for years in all the models we tested. So now we have every model, every method tested with every data set, and we can compute the type 1 error rates, the correct rejection rate, the directional bias, and the magnitude bias.
Isn't there something like
I feel like
Director doesn't like your results.
I know.
It's too many. It's too many.
All right, so that's actually, I don't even need this slide because the whole point of the slide is there are pages and pages of tables like this that give the results on all these metrics for all the models, for all the different ways of doing standard error estimates, and they're just pages and pages, and I'm not going to put them up. So I'm just going to focus on some general themes we learned from this, but you might actually want to look at the tables, particularly if you've used a particular model and you want to see how it does.
Is somebody rolling on a cord maybe?
Yeah, I know.
Well, they're in the ceiling, so...
So no.
So we have a mouse problem.
All right, so the first thing is about type 1 error. And this was, I think, our most shocking finding. We knew that certain types of models, without certain kinds of adjustments, had big problems on type 1 error. This has been shown in a couple of places in the literature already, so this isn't actually a completely unique finding on our part. But the magnitude of the finding was really surprising, and the fact that some of the things we thought would fix it didn't work was also really surprising. So a lot of models that are the traditional, the most common models basically in the field are these two-way fixed effects models. Until like the mid-aughts, they didn't do cluster correction, and then they did. And you can see that the type 1 error is not that close to 0.05. So more than half the time when the null hypothesis is true, it rejected the null anyway, which is really about the worst I've ever seen anywhere. And is it because if you do some sort of correction to make robust standard errors with respect to the distribution of the variance, it doesn't help at all. And if you do a cluster correction, it actually helps quite a bit. And what we're not showing here is that it helps mostly in the case where you've got 35 states. When you don't have that many, the cluster correction doesn't even get you close. But it's still 4 times on average, 4 times the nominal type 1 error rate, completely unacceptable. If you try and do both kinds of corrections, it turns out, at least in the software we're using, which you can read the report and find out more in the codes online, and you can look at what we did, it basically undoes the cluster correction. And it's possible that you're actually getting that in some software where you think you're getting a cluster correction. So, so there's a problem in that it says it's doing cluster correction, but if depending on how you implement the sandwich estimator, you may not get the full cluster correction, or really almost any cluster correction, depending on how exactly you're doing. Anyway, so of all the models and methods we looked at, there are about 8 methods that had type 1 error rates we viewed as acceptable. And the error rates, that's below 0.1 when the nominal alpha is 0.5. So no more than twice the accepting the null hypothesis, or saying a significant result under the null hypothesis. This first one is a negative binomial model with autoregressive coefficient. It's change coded, and there's no state fixed effects. And you can go through, these are the others, these are like the top 4. As it turns out, they were all autoregressive models. They generally did a better job getting the standard errors right, essentially. In other words, it may be better to actually model the dependencies in the data rather than model under assumptions that they're independent and then try and fix it on the backside by doing some magic with the standard errors. So these all got pretty good type 1 error rates. However, all of the models had extremely low power, like distressingly low power. This data is all of the firearms deaths in the United States, virtually a complete census. It's like 99% of them, they believe. So it's disappointing with all the data we're ever going to get to evaluate these laws, essentially. We do not have power to detect the effect we specified. The best power was only, across all of our simulation conditions, only 0.2. It was one of the models that also had acceptable type 1 error. So the other models that had good type 1 error actually had pretty low power. So there was some evidence of directional bias. Most of the models had very little directional bias. The linear models on the rate outcomes had 0 directional bias. But one of the exceptions are these log transformed outcome models, which I said are really popular in the field. They show directional bias. And I can talk a little bit about why that was, but it has to do with the fact that we're looking at bias in regular units, like deaths. And the fact that something's unbiased on log deaths does not mean it's unbiased on deaths, because the bias is generally not the same across nonlinear transforms of your outcome. So, and this has bias in a positive direction. It wants to say the law causes deaths. So it was particularly a problem, like virtually every other problem, the fewer treated units you had. So magnitude bias was a real problem for the autoregressive models. If you used effect coding, if you assumed the autoregressive coefficient, if you use the coding that's unbiased when the autoregressive coefficient is 0, and it's obviously not 0, you massively underestimate the true effects. You estimate them about less than a third of their actual size, and you have a corresponding penalty for power. If you use the change coding, you really had minimal magnitude. In fact, it's a really, really small fraction of the standard error of the estimate. It's ignorable. So the model that performed best overall, best on power, had acceptable type 1 error. Magnitude bias was 5%. Is this negative binomial autoregressive model with change coding and no standard error adjustments. This model we liked for some other reasons. It was almost insensitive to the inclusion of covariates. Controlling for the outcome at the previous year basically captures all the variance you got from the covariates. And so whether you have the covariance or you don't have the covariates, one of the big concerns in this literature is the effects seem to be sensitive to the inclusion of covariates. And that was a big concern, like how do you put them in, how many do you put in? And it won't make much difference here. Unless you put in so many, of course, you get kind of overfit or something. Another advantage is that autoregressive models account for regression to the mean, which is another concern in this literature, that the states that implement the laws were different in their levels prior to the law going into effect, which is a problem for difference in difference models. And so if there is regression to the mean, you're actually modeling it. So the conclusions from our simulation, the broad conclusion, are that the researchers should be really, I don't say wary is very suspicious of trying to correct problems in your models by tweaking your standard errors on the backside. It turns out to be much more finicky than we thought, and even the correct adjustment doesn't actually always get you near unbiased estimate of the standard error. And things that we thought would make things better, like if a robust to the variance assumptions is good and robust to the independence assumption is good, then robust to both would be better, and it is not. So as a general rule, I think I would advise research is if you get the standard errors in 3 different ways, my guess is the one that looks worst for you is probably the one that's right. So the other obvious thing is that when you're using an autoregressive model, in these particular data, the change coding works much better than the effect coding because you get massive bias if you use the standard coding of the variables and include an autoregressive effect. The other sort of general conclusion is when you don't have many implementing states, this whole thing just falls apart. The model that we prefer actually doesn't really fall apart at small n's. It basically maintains its ability at small n's, but because the power goes to 0 or goes to alpha, you can just flip a coin to get your results, right? You have no sensitivity to effect of this size unless you really believe the laws you're testing have big effects, like really big effects. You're not going to detect them in 1 or 2 or 3 states. So that was disappointing because we would have loved to, it would be great to be able to give policymakers feedback after a handful of states have implemented a law. It looks like that might be a bit of a pipe dream, at least on this outcome. So the other conclusion is because statistical power is low, even under the best circumstances, even when you've got 35 implementing states, the power just wasn't very high. It does not meet any normal acceptable standards for power to do frequentist testing. It really calls into question whether you should be taking a frequentist approach in this field. That maybe you should be just trying to get people good estimates and get information about the distribution of the posterior to guide policymakers, rather than saying, I can reject the null hypothesis, or I can't. Because the truth is, you can't most of the time, even when there is a true effect. Like I said, unless you start believing that the law you're testing could increase or decrease deaths by 10%, 15%, something like that. Most of the policies that are being implemented in the state are what you might call small bore changes. They're taking away, in very specific places for very specific people, the right to carry a gun, or how they store the gun for a small subset of the population, or something like that. So we wanted to apply these things to real laws. So we took what we learned, but we decided to make a bunch of changes to the model. So I'm not going to go over these two slides in great detail, but we ended up adopting a Bayesian framework, even though all the simulation was in a frequentist framework. And we're using a somewhat more flexible model in the Bayesian framework. And our preferred model from the simulation is a special case of this more general model that relaxes constraints on the phase-in period to have nonlinear phase-in.